Definitely in mathematics and mathematics too.
But there's a 3-2 program in engineering, right? 3 years here, a couple years there. And so then at some point we had talks with University of Vermont, would there be maybe a 5-year undergraduate / master's program with them? So you would take 1 more year, but it would be a master's class. And the sticking point was is we don't have some master's classes in education, but they couldn't really figure out how to count undergraduate classes as master's degree classes. So it was, and there were 4 credits, the 3 credits were 4 credits. There are a few things like that. Who gets the money? Where does tuition actually go? So there was a few things like that, but it really came down to the other thing. And then if somebody's advanced enough, they can always take a few classes over there. Anyway, so. Okay, so we'll pick up the project today. In reading those, I'll try to catch up on other grading to get problem sets back and things like that. And by the end of the week, there'll be a new problem set assigned for the following week that does something with ANOVA. There's enough complications and different variations on ANOVA that we'll look at some different things, and then that will come in some more bigger investigations in ANOVA. And so today we're going to look again at this chapter 13, which had the 2 data examples we talked about before, but now focus on doing some of the computations. What are some of the formulas? How does it get done in R? And how would you reproduce some of the things that are in the book? All right? And so both of these examples, with these randomized block designs, it's kind of a special case in a way of 2-way ANOVA where you have blocks, and then you have treatments, and you might have interactions. The treatments might work differently in different blocks. You spread the treatments on units within a block so that you get more, you see the treatments under the variety of conditions of the blocks, and you maybe get some more precision because the blocks take out some of the variation in Y. They explain part of the variation in Y, and so what's left over in terms of seeing the index treatment can be more focused. So it's a good design for many cases. Right? And so in this, if we have, I wrote everything, I guess I can write everything. So the things that we have are kind of Y, I, J, K, would be a measurement, an outcome measurement on treatment. I, block, J, person or unit. And so we might have n sub ij individuals getting a certain treatment within a block. Sometimes this is one, that there's no replication, that there's only one application of the treatment within each block. But sometimes there's 2. In the second example, there was the Pygmalion group, and then the 2 platoons that were, so ni was either 1 or 2, depending on that. We're going to let I equal the number of possible treatments. Really the number of treatments in the experiment. And then J, I'll call as the number of blocks. Other people would use different numbers for that. I like to make it as simple as possible to keep it I and capital I and J and capital J to keep track of things. And so there's a sum of squares total that we can compute in analysis of variance, and that's just simply the variability of the y's around the overall mean. So it would be a sum over y, sum over j, sum over k of the y, I, j, k's minus an overall y bar squared. And so this overall y bar is just the sum of all the y, I, j, k's over the total sample size. And that total sample size in formulas would be a sum over the So this is over all I, j, and k. Up here, over all the indices. And this would be a sum over the treatment, the blocks, or the sample sizes in each of those groups. Right? And so that reflects the total variability of the y's, of the individual values from the centers. But this sum of squares total, right? There's some contribution from the treatment, some contribution from the blocks, and if we have an interaction, then there's an interaction effect. And then after that, there's some residuals. Right? And depending on whether we have an interaction in there or not, if it's the additive model with no interaction versus the so-called saturated interaction model, we would do things a little bit differently. Right? So in the sum of squares treatment is the same in both cases. We're going to take a sum over the different values of the treatment, of the number of observations that are given a certain treatment, of the average in the treatment group minus y bar squared. And this y bar I, right, then is the sum over all the blocks of all the individuals that have that treatment I applied. So treatment I. Over the number that get that treatment. And right, so this n sub I then is a sum of over all the blocks of the sample size for treatment I in that block. So in writing out notation with this, there's a lot of subscripts and a lot of keeping track of things. But anyway, this would be the sum of squares treatment. And so if the averages by treatment differ from the overall quite a lot, you're going to get a pretty big sum of squares treatment. Degrees of freedom associated with this is going to be I minus 1. Right? I, different treatments. But any questions on the notation of these sum of squares are looking at? Right? The sum of squares blocks is similar, but with the J subscripts. So sum of squares block is going to be a sum over the blocks of the number of units in the block, and then an average of the blocks minus y bar squared. And in block J, this y bar j is the sum over the treatments now, and the sum over individuals, I, j, k, all with a certain value of j for that block, over the number that are in there, and this n sub j then is the sum over the treatments of the number of individuals by treatment in that block. So if it's if there was just one replicate, I mean, if there's only one unit in each block for each treatment, then this would be capital I, it would be the number of treatments. There are some designs called incomplete block designs where you don't necessarily put every treatment in every block. Right? If resources are really tight and you have a lot of treatments, like we had the 6 treatments, well, if a block, well, you have 6 treatments in that, if instead of a block being 6 squares, but a block was really 4 squares, right? You could only afford to go down underwater and do this design and set things up, you might not have them all, right? So that's a different issue that we might look at another time. Right, so we have a sum of squares total, sum of squares treatment, sum of squares block. So then in the additive model, right, additive model said yijk is a there's an effect for treatment, there's an effect for block plus some error, right? There's no other interaction in there, so we don't decompose the sum of squares into an interaction piece, and the sum of squares error, right, is the sum of squares total minus the sum of squares treatment, right, minus the sum of squares for block. Right? And so you just calculate it that way. Degrees of freedom for error is the total sample size minus the minus I minus j. And I forgot to say degrees of freedom for the blocks. Right. This is j minus 1. This thing plus 1 maybe? I think plus 1. It's like the total sample size n minus, maybe that's not there. What is it? It's either this or plus 1. So in the ANOVA table, I'm kind of confusing the two things, I think, a little bit. So in our ANOVA table, we'd have treatment, we'd have blocks, and we'd have residual or error, right? And then total, right? And we'd have the sum of squares for these things. Sum of squares treatment, sum of squares block, sum of squares error or residual. I'll write error since I wrote it up there. Those things add up to the sum of squares total. Right? Then there's degrees of freedom. This is I minus 1, j minus 1, and this is n minus 1. And so if this is n minus I minus j plus 1, right, then those things will add up. So right, you add I minus 1 in there, right, and then j minus 1, so that would add up. Right? And so then the mean squares are the sum of squares divided by their degrees of freedom in these three cases. And we can do two F statistics, where we can test is there an effect of treatments and is there an effect of blocks. And both of those are tested relative to the mean square error. So if this is mean square treatment, mean square for blocks, and mean square error, we can test, is there any treatment effect by the F statistic as the mean square for treatment over the mean square error. Also, we can test, is there an effect of blocks if we're interested in that. Mean square of blocks versus mean square error. And so both of these have F tests. The degrees of freedom are related to the degrees of freedom there. And if we get sufficiently large F statistics where we're going to reject the hypothesis and say that there is an effect here, and the coefficients that would be in a model that would have a treatment effect or block effect are non-zero. In other applications of two-way ANOVA, we might have treatment factor 1 and treatment factor 2. Right? So in addition to the organisms that are down there, right, we could be interested in, if this was for thinking about how can we set up a business to grow seaweed to feed the world and things like that, we might think about fertilizers or additives to be put into the environment. So we might have, do we restrict the big fish from getting in and eating everything? And then do we add something to help the seaweed grow that we're eventually going to harvest? So blocks might be replaced by, a second factor that would have different levels. And the same thing would be done, right? The same kind of composition. So that works out if there's an additive effect, right? But once there's residuals, once there's an interaction, this model is called saturated because it has as many parameters as there are cells once we cross blocks by treatments. It has an effect for each block times treatment, and it's as many as we can possibly put in given these variables. Their sum of squares total is the same. Sum of squares treatment's the same. Sum of squares block is the same. Right? But now there's a sum of squares for interaction. Well, kind of following the patterns before, each block times treatment is defined by an I and a J. Right? A certain level of treatment, a certain level of block. And there's a certain number of observations that get that measurement. Right? And so it's the average in that block over the average squared. And the sum of squares error could be done by subtraction if you take the total minus these two, but there's also a direct formula. Right? You can take the yijk values minus the average in its cell, right? Just within its treatment block combination, you get that. And now you get, you put it into the ANOVA table like we'll see in the computer output, right? You get a line for treatment, a line for block, a line for interaction, and so you essentially get 3 f-tests right from the start. They're all compared to mean square error, right? But that's kind of what's going on with some of the different decompositions depending on which model is useful, right? So without writing a lot more, some of those things are reproduced in the book in terms of setting up. Okay, let's look at it as an example. So we want to see how R does the computations and think about plots and how would the plots help you see the size of the interactions. And there's a little kind of weird wrinkle that happens with this additive model we want to kind of think about. So this first data set was the seaweed grazers. There's blocks, which were different environmental conditions, different positions in the water, in the intertidal zone, and then the different treatments. And this is what was allowed in. So the control, nothing was allowed in. The limpets is capital L. Small fish are let in, or limpets and small fish and big fish, or all 3 are let in. So there's 6 of the 8 possible treatments because we can't exclude the big fish. We can't let the big fish in and keep the little fish out. That's the way to do that. So we might look at the averages overall. The overall average is 28.625. Right, so that's percent cover with seaweed. If we have attached the data set, right, you can see what's kind of there. Right? There's a few standard things that are there, standard statistics, standard graphics, standard data sets, standard methods, things that are always there. Right? But now my case 1301 data set is there. So as I use it, right, if I type any of the cover, block, or treatment, it will know what to do. Initially I attached case 1302, thinking that maybe we would use those, and case 1302 also has a treatment, so that's a duplicate variable name. It's actually caused me a little problem, like attaching them both. Right? When I tried to split and summarize things by treatment, they thought, oh, it's cover on this data set and treatment on that data set, and they're different lengths, so that doesn't work, right? So I had to detach that data set and just do one at a time. Anyway, that's more of a little R thing. X-bar treatments, you can split the cover by treatment and take the means, and this will give you the different means, right? And so percent cover in the control, 52, when all 3 seaweed eaters or grazers are let in there, it's pretty low. So just looking at the means, there seems to be kind of a big difference in percentage. Right? By block, you can split it again. By block, there's some variability by block, 55 down to 9, but there's a lot more kind of here in the 20s or so. It doesn't seem quite as polarized as this. So maybe that'll come up as being significant or important or different. How many treatments are there? There's 6 treatments. How many blocks are there? This unique command in R, treatment is a factor, or it would work with character strings, or levels, you know, if they're too numerical, but how many unique values are there. In working with these type of character strings or factor variables, there's a unique command and there's a levels command, and they'll give you back some basic summary information. You might also, you know, table is also a command that's useful for these things. So there's a table of these counts. There's 96, right? There's actually 48 possible different cells. So in each block, there's 2 copies of each treatment. Right? So I often find it's useful to see that structure, these some category variables and how they relate to one another, how things are set up. If there were some zeros in there, that would be kind of a concern because you couldn't estimate anything in there. But in survey data or something that's not a designed experiment like that, if you get a table where, you know, there's huge numbers and a few cells and everything else is 0, 1, or 2, or 1, 2, 3, then that's really sparse. If you're trying to estimate differences or summarize things, it gives you a key clue that you might want to group categories together. So it's always good to look at that. I wanted to calculate, so this thing X bar cell, I want the averages of my of the outcomes of the cover by block and by treatment. Right? I want to see what those averages are. So how can I do that efficiently? Well, if I set this thing up, I'm going to, so when I did this thing, right, X bar TR, X bar TR, right? So here's my treatments are in this order, right? X bar block is in that order. CL, L lowercase f, and so on. That's the order they come out when I do that command, right? So when I want to do my two-way array of averages, I want them to be in the same order. I don't want it to mess me up. Right? So it's a kind of headache. Unique and levels do things in different order, right? Levels will reproduce the order that's in the factor statement. It's a factor, the factors are in a certain order. But unique will just go through the data set and take the first one and the next one, and if there's repetitions, it keeps moving down and reports that order. So it's just a little bit different. It doesn't necessarily sort them. You could sort them and get out of that. But so here is the blocks, just 1 through 8. The treatments, though, their unique levels are here, and it's a little bit different than what was in my X bar. CL, oh, it goes little f for this. So there's a little bit different. So you want to be careful how you keep those things. That's only a kind of a programming thing if you wanted to pull out means and do detailed things, which will be important when we do contrasts. We want to do contrast between means. We want to make sure we know which one we're talking about, and the right X bar value is entered there. We have the right sample size as well. So levels, though, does match that order. So I'm going to do a little programming loop through my treatments, through my number of blocks, and the average value in here of cover. I'm going to take the values of cover such that the treatment equals a certain level of treatment and the block equals a certain level of block. Right, so that will match, and then it will take the average of the 2 observations that are in there. Right? I'm going to put labels on this. A matrix like this, you can put dimension names or dim names on there, and it's a list. Row names, column names. And I'm going to do the same levels that went into here. Okay. And then in this X bar cell, once I do that, this thing runs very fast. And then dim names in the X bar cell gives me my averages across all of those. And they should be sorted correctly. There's 2 in each of those, as I said. So those will be getting the raw numbers that might be useful for later, or putting into a table to summarize for presentation. Here's a box plot now of what things look like by treatment. Does there appear to be a treatment effect? Yeah, I think it looks like it'd be a pretty big treatment effect, right? So if limpets particularly are in here, that's kind of low. This is the control with nothing getting in. Right? If they all get in, it's the most low. So there seems to be a pretty strong effect. And maybe the effect is not the same based on which letters are there. Right? Small fish by itself is not too much different from control and so on. Is there a difference by blocks? It kind of looks like there's a difference by blocks, right? But there's pretty big variability. Well, there's a couple blocks that are lower, and then it's not quite as distinct, right? As the previous picture. Right? So the previous picture had that, and this one had this amount. Right? If you paste some character strings together, right, it's going to put the TR value and then the block value together. So you're going to end up with 48, because there were 6 and 8. You're going to get 48 unique values of that, and so you could do that, right? So these are the LAS tilts the labels. So if you figured out how to make them on my full screen, then you can actually see all the things there. Right? So each of these is based on 2, so they're pretty noisy. Some of them have pretty big spreads. You can add little line separators in there. So this one does blocks, and then with all C's, blocks with all little f's, and so on. So there's 8 in a row that are one type. And so it actually puts these things at 1, 2, 3, 4, 5, 6, 7, 8, and so on, numerically. So you can put little lines in there. So this is control, little f, ff, and so on. And then the limpets with everything is actually down here. So in this order, you kind of see some effect there. Kind of picture it more. If you switch treatment versus block, right, then it's going to put the BL first and reorganize it. If you put lines there, now there's only 6 treatments within each block, each one 2 times. So if you kind of figure that out spacing, these are the blocks and the variability within the blocks. Right? It's kind of a similar pattern, right, going down across those. So there's some kind of similar effect, qualitatively at least, by treatment within blocks, which is kind of interesting to kind of visualize. But anyway, the book has other graphs that I'm not sure how they made. There's much advanced graphic software and things like that. But with R, with a few commands, not necessarily using ggplot and other fancy packages, you can still make reasonable graphs to show things. You'd have to fiddle with the size of these to try to get them all in there. But on a full screen, it shows up, or full page shows up much better. So now that we've looked at things, if we run the ANOVA command, this is the additive model, right? That has the treatments and blocks. Right? If these had not been called treatment and blocks, but had been called other things, right? If this had been called organisms and environment or something, right? Then those names would be down here, but would have the meaning of treatment and blocks. Right? So degrees of freedom, right? 6 treatments, so 5 there, 8 blocks, so 7 there. The total was 96, so 96 minus the 6 plus 8 would be 82, but you add 1 more in, right? So that's 83 there. Right? And it gets the different sum of squares, mean squares through dividing. Right? And the F values are the ratio of this mean square to 131, or this mean square to that. Both rather large, right? And then it would use a F distribution with degrees of freedom to do the test. So for instance, the probability, 1 minus the probability, an F probability, the chance that you're less than 35.092, right? And it's nice, it prompts you, you want 2 degrees of freedom here. So for testing treatments, it's 5, and then 83, oops, 83. And that should give a p-value, it's about 0. So I don't know, it's not going to show you too much, but it rounds to 0. If you wanted to see that, say if we multiply by 1,000, but we show us any numbers. Well, let's do the other one's not quite so far out there. So 20.78, but this would be 7 degrees of freedom. The denominator is still the 83. 6.66, so it's kind of close to that. I don't know. Whatever. It's hard. Those are very small values. Right? What you also could get out of that, right? Okay, so if you added the degrees of freedom, the total row would have 95, and this would be, if you add these up, you get this, right? This ANOVA object here, this is a little square matrix that's in there, right? And so if you add these 3 things together, that's adding the first column, you get 95. And if you add the second column here, you get the 5302, right? And so for ANOVA, you can calculate kind of an R squared as well, just like, right? So the sum of squares for block plus treatment over that, or 1 minus the sum of squares for, so this is row 3, 1, 2, 3, and then the second one is that value, 10,902 divided by the 53 is about 79%. So almost 80% of the variability in cover is related to block and treatment, just as an additive model. Right? That's really quite a lot of the variability of seaweed cover. Right? The sigma, the standard deviation in the model, right, is the square root of this mean square error. Right? That's the errors are always estimating variances, and so if we take that number, that's the 3, so third row, third column, that value there. There'd be other ways to reference it. Maybe you could put residuals as a row name, and then mean square as a column name, and it would come out. But you can look up. And so that's 11. So kind of an average, plus or minus 11, kind of is a typical thing there. All right, so there's significant treatment effects, significant blocked effect. If you, the way it's implemented in R is a linear model command. It's the same as the regression command. So instead of doing ANOVA, you can just summarize it like a linear regression. Right? If you summarize it with linear regression, it gives you all these coefficients. Right? The average overall is about, well, is estimated, this intercept is 32.875. And treatments, if there's limpets in, then the average cover goes down. If there's limpets and small fish, the average goes down, and so on. And as you go to different blocks, the coverage goes up compared to the first one. And if you read in the book about what these mean and knew the biology, then probably that would make some sense to what's going on. Right? And many of these individual ones are significant. They're very well could be like the block 2 is not significantly different from block 1, but you wouldn't really take out one specific block in that. You kind of deal with the whole design cohort together. In the future, you might consider, was block 1 and block 2 really that biologically different? In another experiment, you might come out and say, well, we only need 7. And that's going to save us some resources because there's not really a difference between growth in these two that are close together. We should really spread them out. So you might pay attention to that and learn something. Here's residual standard error, that's sigma. R squared is the R squared that we had before. Right? But once you're doing ANOVA, right, there's this underlying model, so we should check some assumptions. Right? We've seen the differences between the groups. Maybe there's an outlier, some differences. It's hard to say some things because there's only 2 per block treatment combination. There's not a lot of variability. They can either be close together or far apart, and it's just kind of random. It's hard to say too much. But you could look at the histogram of residuals. Do those look kind of normal? Not too bad. Not too bad, right? Maybe a little more clustered in the middle than, but that could be kind of an artifact of the spacing of these things. You could also do a QQ plot, and you can add the line to it, right? So it's a little bit tilted off of that, right? That could reflect that some of these, so these are the theoretical ones, they don't change. They're based on sample size and the theory. But these could either move up and down. So it looks like these are a little bit large and a little bit small here, right? Which would kind of reflect a little bit more spread than you would typically think of. So it's not too bad. Probably those p-values that are so small are pretty reasonable indications of very significant effect. We can also look at equal variances. Do the residuals look the same by treatment and block? So by treatment, do the residuals look kind of similar in spread? Not too bad. They're a little narrower in some than some, right? So it's not perfect. Maybe the control or everything, maybe there's a couple different variances, but it's not completely ridiculous in there. So I don't think the model's terribly sensitive. There's some deviations from that. If you had a couple of these that were, several times the size, then you would worry about just fitting one model. And maybe you should have separate models for things that are very, very different. By blocks, there's one block that seems to have bigger variability, but the others are kind of similar. So I wouldn't get overly worried about it. We can also do an ordinary residual plot, right, for fitted values versus residuals. This is what we get, and here's the 0 line. Right? This one, right, has a little bit more of a pattern, right? So a little bit more non-normal. It's clearly bigger here, and more spread in the middle. Right? Well, maybe this affects the conclusions or use of this model a little bit, right? One thing that could be going on, right? What is percent cover? Right? It's 0 to 100. It's bounded, right? And so you can only get, to that point or this point. So the predictions are differences from that. So if things are clumped against one of the sides, you could get that, right? So there's kind of a pattern there. The book suggests transforming cover through this logit transformation, and results in the book use that. Right? And once you do that, this transformation, right? So cover divided by 100 minus cover times log. This transformation takes that 0, 1, or 0 to 100 interval and stretches it from negative infinity to positive infinity. So you don't get these boundary issues of being stuck up against the side, right? So that might be a good thing to do in the analysis. If that's so, you kind of start from the beginning and compute this R value and look at it. I didn't go back and redo those things, right? But is there anything else kind of funny about this besides the pattern? Right? What's the range of the fitted values? Are we getting some negative fitted values? Right? You show this in a presentation to biologists and say, wait a minute, you can't have negative seaweed cover, right? It's not rock or coral forming or something like that, right? So but then it's negative value. Is that an error, right? Does that show up as something that's implausible? If you summarize the fitted values, you do get some negatives, right? This is negative 11%. The cover values themselves go from 1 to 95, right? So how can we get a negative fitted value? Right? In this. And is this an error or something, or can we explain it, right? So how do we get negative fitted value in the additive model? So understanding this helps us understand a little bit more what's going on with the additive model. Right? So what's a prediction? So there's a beta 0 hat, plus there's the effect of a particular treatment, so IJK, plus the block effect. So there's no interaction in this model, right? So there's going to be some treatment effect. So if in general, a particular, having the lipids in there causes a big decrease, that's going to be negative, right? And in that block, right, the block effect is that entire block, right? Not just that particular treatment, right? So some of the blocks also had less growth, or not much growth. So the treatment is across all the blocks, and the blocks are across all treatments. So you can end up with combinations where the treatment effect is maybe coded as negative, and it might be quite negative for some treatments. But the block effect therein is only moderate. Right? And you put these things together, and so it can go negative. So let's look at the regression output to see if we can see where that is, right? So in the regression output, here are the estimates, right? The overall estimate is 32.875. Treatment with L goes down 32. Treatment with L and F goes down 35. Treatment with LFF goes down 44. Right? So the intercept with this treatment is negative, right? So that's kind of the aggregate difference. And now we apply that in every single block. Right? But in certain blocks, like block 2, there's only a little bit more extra growth. Right? So you pick an estimate of the overall treatment effect and the overall block effect and put them together with the intercept, and you can, you pick one of these and add that to it. So you can end up negative. Right? So it's not an error, it's just a restriction to that model. Right? If you did the Logit transformation, you're not going to be, there's no 0 to 100 barrier, so that kind of avoids that issue. But in linear regression, with these indicators, you can end up producing things outside the range. It doesn't know that you can't do that, and it can't stop it, because in that linear model framework. It's not an error, it's just, that's just what it's doing. So anyway, it's there. So it can do that. That might be uncomfortable to try to explain. I had something like this come up in a consulting thing on a large-scale survey. So in this large-scale survey, we do non-response weighting. And the non-response rating is not necessarily at the smallest level of organization of the survey. It's at the national level and some parts of the subnational level. But then, so when you look at certain subgroups, they can produce abnormally large swings in estimates because their weights from year to year are not determined by only the local area, but more broadly. There's just no getting around it. If you have the implications of a model or an adjustment at the gross level can produce funny things at the micro or local level. But anyway. So, yes, we do get some negative predictions there, and that does come up in the plot. both treatment and block were successful, so we could consider interaction. So this is the command that does the previous one does this one up. Right? This is the ANOVA with the interaction. By putting that star there, it does treatment, block, and then the interactions. Right? Treatments, the sum of squares treatment there are, right, these first two rows are the same. Sum of squares treatment, sum of squares block are same as before. But now we have a sum of squares interaction. And if you add those two together, right, you get about 10,900. The sum of squares residuals before is now broken into these two pieces. Okay? And the 83 degrees of freedom is broken into a pretty big degrees of freedom for the interaction and then the residuals. Right? So then we compute mean squares, dividing along. And now when we test this mean square versus this error is a lot smaller, right? Because we've pulled out that interaction, right? So the effect of that interaction is to make this, what's left over, massively smaller. So we still get a very big F value. This one, it was 20 before, now it's 30 because this is so much smaller. And we can also get this line for testing, is there an interaction? And it appears there is a significant interaction between treatment and blocks. Right? In some places, in some treatments, have a big effect. In blocks, where, yeah, anyway, it's just variable, right? So, wanted to get that. For testing, if you wanted to test the just additive model versus this model, there, I mean, if you, this is a test that says there's a significant interaction. But you can do that that extra sum of squares F test. Right? You can use the sum of squares and degrees of freedom from the smaller model, which is this one, versus the sum of squares for this interaction model. That includes the interaction here. And it will test that. And so it takes the differences of sum of squares between the two models, the differences of degrees of freedom, and does a particular F test. And it's the same as that one. So the interaction is significant. It should be included in the model to explain things. Right? But we might want to test, still report an overall test of treatment. Right? So instead of testing treatment by itself, just using that line, it's important to test the overall effect of treatment, because it interacts with block. Right? So you can do that as another specific ANOVA test. Right? So this only has block, no treatment effect at all. Right? And this one has treatment in there with a main effect and an interaction. Right? So this will take a difference between the sum of squares, differences of degrees of freedom, and give you a significance test there. Is there any treatment effect either through the main effect or the interactions? Right? And so this one, incorporating the interaction, once we see that it's significant, would be the right one to do for testing that treatment. But once we have that, so there's no question that there's this big effect, we might want to do contrast. Right? There's a nice example in the book because the contrasts are motivated by biology. Is it just the big fish? What's the difference between little fish and big fish? Is there interactions of some of these treatments? Are they different at certain blocks? Right? So we can really think about what those mean. Right? To set up contrasts, we need means, sample size, and sigma hat. And then a contrast vector. Page 399 of the book does a nice job of laying out some contrast vectors. The order that they put in their treatments is different than the ones that I've done. So if you want to use their coefficients, you have to translate these, just rearrange the order to match what R is doing. Right? So the sigma we're going to take is the estimated root mean square error from the bigger model. Right, the one with the interaction. So it's 9.4 something, right, instead of the 11 that was before. Right. So once we have the interaction, there's less variability left over. Right. The degrees of freedom we need for a t-test, these are all 1 degree of freedom t-tests, specific contrast t-tests, is the t-test from the residuals under the bigger model. So, right. So we want 48 from this bigger model, right? And so you can pull that off. It's the fourth row, first column, or you could just type 48 if you read it from the output. Right? But it's there. So I did the means before. Oops, went to the end. I'm kind of near, there it is. So the thing I want to look at, right, so we're going to use called X-bar treatment, right? Here's the averages for the treatments. Each treatment was done 16 times, right? Because there's 2 of each at each of the 8 blocks, so 16 is the sample size for each of these things. And if we want to do large fish versus small fish, well, there's no fish in here allowed in. So I'm going to put a -1/2. There's 2 treatments that have small fish only, and 2 treatments that have big fish. I'm going to put a -1/2 when it's a small fish are allowed, and then +1/2 when it's these big fish, right? So these things correspond to the particular order of the beans, right? So I just call that C1 for contrast, right? What I'll do with that is I'll take the C1 times the X bar, right? So if I take C1 times the X bar that I calculated for treatments, it zeroes out those 2 that aren't relevant, makes a couple negative. If I add those up, I get a contrast average of -9. And I'm going to compare that to a certain standard error, right? You're going to square the C's, divide by the sample sizes, multiply by the variance. That ends up being the variance of this particular contrast. The 16 is because there's 16 per treatment, right? And this is the sigma that I stored. Take square root. So that ends up being a t-value of -3.81. Right? So already you know that's pretty big. So I save the t-statistic as something. It's negative, so I'll take the absolute value, and I'll take the probability it's less than that, and use the degrees of freedom, that was 48. Until I get a p-value, it's practically 0, right? It's not likely to be beyond 3.5, 3.0, right? And this is 3.8, so it's highly significant. So there is a big difference between small fish and big fish, right? From the graph, small fish didn't make that much difference, but big fish eat a lot of seaweed. So that'd be a contrast, right? So kind of being strategic and saving means in certain ways and keeping track of order. And it's not that cumbersome to really look at some different contrasts. It takes a little programming, keeping track of things, bookkeeping. We could look at small fish versus no fish, excluding large fish. So if we exclude the large fish, the limpets and the small fish can get in. But should you also exclude the small fish in there? Again, there's 2 treatments that have small fish, 2 that do not have small fish. So I'm going to put -1/2, so 1/2 kind of average those 2 together. Zeros for the cases that do not have those small fish, so that's my C2. This one, again, there's 16 per treatment. And I get a t-value that's also pretty small. Its p-value is 0.014, so it's not quite as significant. This statistic right there, and that's the things that are modified there. If I had done this again, I probably would have saved the t statistic like this, and then just typed t-stat to get it. Because when I changed C1 to C2, I had to change this thing in 4 places. I could have done it with changing it only in 2. Or if I had done them one after another and defined one contrast, I could have just called it CON for contrast, and then not had to retype that code at all. I could have just changed CON to contrast of it. So, if you're doing these things on big scales, you can try to make it a little more efficient. The third one here, limpets versus no limpets. In this case, there were 3 that allowed limpets in and 3 that allowed them out. So instead of doing 1/2, I'm going to take 1/3. It doesn't really matter what those are, as long as the treatments, the weights, these contrast weights, for one side match, the total matches the negative of the other total, right? So they add up to 0, right? So I could have made all these 1s and negative 1s, and then they would have added up to 3 and negative 3. It's both in the numerator and in the denominator, and so it would end up canceling out, right? In terms of that factor. But anyway, that's the third one. The limpets versus no limpets also is terribly significant, right? They have a nice table in the book that does this for this example too. It does use a transformed R value, so that the results are a little different, but they're not too terribly different. They're kind of significant in the same way. You can do contrasts with the regression model, but there's a little subtle thing, right, that in there. If you only include parts of the data in the model by selecting out only certain effects, it estimates a sigma squared. Right? It estimates a residual standard error. But if you have only effects for the different, if the model's different, then that sigma has to be a little bit different, right? In this one, with the fully saturated, you could argue that that's the best estimate of the sigma squared, so it's good to do it this way. But the other ones probably give you similar messages. So there's a little subtlety there, just like the predicted values can be negative. I don't think the predicted values can be negative in the saturated model, right? Because it includes an average for every cell blocked by treatment, right? And those are all positive. So if we do a table, say, of, let's just do summary, of the fitted values from that bigger LM of cover as a function of log times treatment times treat. Yeah, those are all positive, right? So when you allow that interaction in there, then it essentially gets reported the average by block, and all those are positive. So the saturated model does not cause that, have the potential to have that little artifact there. It doesn't always produce negative values, right? So if there's all high averages and there was a relatively small treatment effect or relatively small block effects, comparison to the, if the cover had been on average 85 for all those, and then everything else is a kind of effect of 5 or 10%, it's not going to go above 100. If it's at 50% and plus or minus 5 or 10, it's not going to go below that. So you could have other scenarios where the data just don't produce negative or anything outside the range. But this one it did. Right? You can look at more complicated things, is like the effect of a big fish different in blocks 1 and 8. I just think this one. So there's 6 treatments in block 1. 6 times the big fish appear in block 1. 6 times the big fish appear in block 8. So there's 12 times in all that the big fish appear. There's 8 treatments in block 1, but there's no big fish. There's 8 replications, right? And then there's 4. There's 12 in all. 8 have no big fish and 4 have big fish. So you kind of have to count up how that goes. So because I don't think this line is true anymore. So because there were 8, I made these 1/8 in those, and then I made it negative 1/4 in those others. Well, anyway, there's a little bit more to set up. The contrast matrix that's set up is this thing, right? And so it's positive and then negative for this contrast here, and then negative and positive for the ones over here. And it's all balanced out. And I put it 0 for all the other ones because I don't care about them for this particular question. That one, there it is. You do the same thing. You get a t-value that's only 0.124. It's not quite significant, right? A p-value of 0.22. Why is it? Well, if you look at the averages of small fish in the 2 ones here, B1 versus B8, there's a big block effect This is the average with the large fish. They are smaller, but they're kind of in the same direction of those. So, you know, it's kind of a tripled. Yeah, it's almost tripled here, almost tripled here, and so it just given the sample size and variability and everything, that one didn't end up being significant. Right? So there is an interaction overall, but that particular one did not quite pan out. If for some reason you're interested in that, you know, you can do more complex stuff. So the purpose of this is kind of lay out a few formulas to see what's behind a little bit of this, and go through a few more detailed computations. And Friday we'll keep looking at variations in these NOVA models. So if you have projects, I know that I'm talking about a number of them today. Thank you very much. I'll get them back on Monday after reading them. Yep. All right. Good one.
See Friday.
Yep. Go work on that triple major now.
No.